So if we have a system that has one input and one output, single input, single output, or SISO system, for which the governing equation between the input and output is a linear ODE and time invariant, then the transfer function is defined as the Laplace of the output divided by the Laplace of the input, assuming zero initial condition. What does that mean? So here, let's say I have a system, right? This is my system. Input x, one single input, x of t, goes in, and output y of t goes out. And the relation between output and input, the differential equation governing the behavior of the system, is linear and time invariant. What does that mean? Means that in the differential equation between x and y and t, you only see linear terms of y and derivatives of y. You do not see any terms like y squared or y dot squared or y double dot squared or y times y dot or a square root of y dot. It is linear, okay? So just to make sure that you know everything, I'll give you a couple of examples to refresh your mind about these two terms, linear and time invariant, in DFQ that you should have seen. Just refresh your minds. By the way, as we saw last time, the Laplace transform is used to solve differential equations, but the main point was what? Laplace transform can only act on linear differential equations. If you have a nonlinear differential equation, you cannot apply Laplace transform to it. So it is only useful for linear systems. That's why here we also emphasize, since the transfer function is Laplace of output over Laplace of input, in other words, you're applying Laplace to the governing differential equation, your governing differential equation has to be linear and also time invariant. So let me give you a couple of examples here. So if my governing equation is something like this, y double dot plus 2y y dot equals x squared. What kind of differential equation is this? So x is input, y is output, time is the implicit parameter here. So what is it? Or independent parameter. So what kind of DFQ is that? Yes, it is nonlinear because I have two terms multiplied. If it was also something like this, still would be nonlinear because I have the nonlinear terms. Now, what about this? If I have something like this, is this linear or nonlinear? Well, here x is a function of time, right? X is a function of time. So this is a function of time times the unknown output. So this is linear. So remember, although I have two things multiplied, but those two things multiplied, they are not the unknown function and its derivatives. One of them is a known input function. So this x is known. It's not unknown. I'm not multiplying two unknowns together. I'm multiplying a known by an unknown. X, remember, x is given. Y is to be found. So this is linear. Or if it was t instead, if I had something like this, what is this? This is still linear. So if any function of t is multiplied by y, y dot, or y double dot, or any derivative of y, that does not count as nonlinearity. It's linear, okay? Only when y and its derivatives are multiplied, raised to a power other than 1, or anything like that, sine, cosine, that's where they are nonlinear. So these are linear. These are nonlinear. If the forcing function on the right-hand side is anything that is a function of t, okay, and it's not 0, then this one we call it what? This is non-homogeneous, right? Because the right-hand side is not 0. If the right-hand side is 0, then that is what? This is a homogeneous ODE, correct? Now, what about invariant and time invariant and time variant? If the coefficients of the unknowns, y dot, y double dot, if those coefficients are constant, we call it an ODE with constant coefficients. If they are like this, time dependent, we call it time variant. So this guy is what? This is this bottom one, actually, or the top one, because x is a function of t. So here, because of this coefficient, which is a variable of time, we call this time variant. What is the order of your ODE? The order is the highest derivative term. So the order is what? 2. So I just want to make sure you know this. You didn't forget them. So if I say what kind of ODE is that? This is second order ODE. It is linear. However, it is time variant and it is homogeneous because there is no term on the right hand side. Okay, what type is this one? Again, second order. It is linear, but it is time variant because this x is a function of t, and it is non-homogeneous. These are all nonlinear. And the one that we can use for Laplace transform and finding the transfer function are the ones that are time invariant. So ODEs like this, y double dot plus 2y dot plus 3y is equal to x dot minus x, something like this. This is what? This is linear ODE. There is no coefficient that is a function of time, so this is time invariant and it is second order. Okay, so please keep that in mind. Second order linear time invariant ODE. On this guy, I can apply Laplace transform, then assume 0 initial conditions. Let's put the plus here. I can apply 0 initial conditions and then find the Laplace of the output over the Laplace of the input and call it the transfer function of the system. So in this case, if I apply Laplace to both sides, what happens? You know, Laplace of y double dot in general is what? It is s squared Laplace of y minus s times y at 0 minus y dot at 0. Okay, this is Laplace of y double dot plus 2 times Laplace of y dot, which is sys minus y of 0, and then plus 3 Laplace of y this is equal to Laplace of x dot plus Laplace of x, and Laplace of x dot is s x of s minus x at 0 and Laplace of x. Okay, so I have applied Laplace to both sides of my governing differential equation. Now I assume 0 initial conditions. So any initial condition I have, I assume they are all 0. So if I now factor it out, I will get y of s times, you can see there is an s squared term here, and then you have plus 2s, then plus 3. This is equal to x of s times s plus 1. And from here, I can find the transfer function if I show it by g of s, which is the Laplace of the output divided by Laplace of the input, which in this case is s plus 1 over s squared plus 2s plus 3, okay? So transfer functions are typically rational functions like this. And so now I can write it up there in that box. So if I know the input in time, or equivalently, I know the input in the S domain, and I know the relation between output and input, or the ratio of output and input, g of s, which in this case it is s plus 1 over s squared plus 2s plus 3. So if I know this one, then I can find y of s. And so when I know y of s, I can find y of t, okay? So again, we have this very important rule which says from a cross multiplication, you can see the Laplace of the output is equal to what? Laplace of the input times the transfer function. Okay, this is very important because input is typically given to us. G of s is an inherent property, a characteristic property of the system. The important thing with G of s is it does not depend on what type of input you give to the system. It is always the same for the system, regardless of your input. At least for a linear system, the transfer function is constant, and it is determined by the governing differential equation, okay? So it does not depend on input. That's very important. So once I know what type of system it is and what is the governing equation, I can find g. X is given to me, therefore I can find y, and once I know y in the S domain, I apply inverse Laplace and I find what? Y in the T domain, right? So that's what I do. That's the overall idea. Okay, so I summarize. Your governing differential equation has to be linear in order to find a transfer function. It has to be time invariant. All the coefficients should be time invariant. The Laplace of the output over the Laplace of the input, we call it transfer function. If when we do Laplace transform on the governing equation, we use what? Zero initial conditions. Okay, we call it transfer function. Again, it is an inherent property of the system. We saw it is a rational function. The other important thing we need to know is in a causal system, this is what I mentioned in the previous lecture, the order of the numerator m, the highest order of the polynomial, is less than the order of the denominator n. Why? And what is a causal system in the first place? Causal means the input is the given to the system, the output is the result, or the input is the cause of the output. So in order for a system to have output, you need to have an input, right? Cause and effect. So let's look at an example here. So if the order of numerator is bigger than denominator, so the system is not causal, okay? So if you have a non-causal system, where the order of numerator is bigger than or equal denominator, for example, g of s, let's make it very simple, is s, or s over 1, right? So here, m is 1, the highest order, and n is 0. In the denominator, there is no s term, okay? So if g of s is s, we'll talk about what S means. It's a derivative. But what does that mean? So here, this is equal to y of S, the output over input. Now here, let's go with the same thing. So I use x for the input. So y of S over x of S is simply S, a non-causal system. What does that mean? If I cross multiply, I will see that y of S is going to be S times x of S. Right? So I cross multiply this one with this one. And if I take inverse Laplace transform and assuming zero initial condition, right? So if I assume zero initial condition, I can basically add minus x of 0 here because that's 0, right? I'm using zero initial condition. So now if I take inverse Laplace from both sides, the inverse of y of S is going to be y of t, excuse me, and the inverse of this is basically d of x of t over dt, right? Or x dot of t, basically. So as I said, the output is the time derivative of input. Now, why is it that the system is not causal? So what is the definition of derivative? Based on what you learn in calculus, that's the limit of x at t plus delta t minus x at t divided by delta t, as delta t goes to what? 0, right? Now, what does this mean? Means at the current moment, if I want to know the output of the system, if I want to know the current output of the system, and if I can approximate this by some very small delta t, so let's use a very small delta t, very small, and say this is equal to x of t plus delta t minus x of t divided by delta t for a very small delta t, right? Much, much smaller than 1. This means very small, like 10 to the negative 5, 10 to the negative 6, right? So what does that mean? In order for me to be able to calculate the current y, what do I need to know? I need to have a time difference. We call it an interval, right? A sample time. So I need to have a sample time. I need to have the current input. Right, so this is current output. Now let me ask you this. See if I can zoom out. What is this one? What is this? Since delta t here is basically less than 1, very small, but still bigger than 0, what does it mean? What x is this? It's the x of current plus a little bit forward in the future. So this is what? This is future input, actually. So what does that imply? Means in order to find the current output, not only I need to have the current input, I also need to have what? The future input. While a causal system, the definition of a causal system is what? Current output is only determined by current input and previous inputs, not future inputs, right? Correct? If your system is waiting on future to determine its current situation, that's not causal. Causal means whatever you have done in the past and whatever you're currently doing is determining your current status. Whatever you do in the future is not going to be retroactive and it's not going to affect your current situation. Yes? That's a causal, a meaningful physical system. In physical systems, the future will not come and affect our current situation. It's only our past and current that is affecting our current situation. So you see clearly here that if I have any, I gave you one example, a simple example, but I can show you in any other case that the order of numerator is bigger than or equal denominator, especially bigger than denominator. The problem will be that your current output will depend on future input, and that's not going to happen in a real physical system, in a causal system. So in this course, we always assume that our transfer function belongs to physical systems, at least the one that we do for physical systems, because you can always mention something like this. But for physical systems, the order of numerator is less than or equal denominator. Now, a few more points about transfer functions. So we learned that transfer function is what? It's a property of the system itself. It does not depend on input. I mean, regardless of what input you give to the system, the transfer function is the same. So what will change? Of course, the output, right? So let's make it very simple. The transfer function is simply 2, number 2. What does it mean? The output is always what? Twice as much as input. So this 2 is the same. Now, if one time you give it 5, it gives you back 10. If you give it 4, it gives you back 8. You give it 3, it gives you back 6. So different inputs will generate different outputs, but the ratio is not going to change. It's constant. It's a property of the system. That's one thing. 2, what if the system does not have one input and one output? It's not SISO system. It has multiple inputs and multiple outputs. We call it MIMO system. Then what? How do you define transfer function? Well, in this case, you do not have a single transfer function. You have a lot of them, and actually you have a matrix of them. For example, here, you have M inputs and you have P outputs. Then you can easily show that you will have a P by M matrix of transfer functions, okay? A simple example will be like you have a system here, and this system has 2 inputs and 2 outputs. Or let's say it has, let's just make it simple. So U1 and U2, right? 2 inputs and then 2 outputs, Y1 and Y2. So do you define one transfer function? No, you define one, which is Y1 over U1. Then what? 1, which is Y1 over U2. Then you define Y2 over U1. Then you define what? Y2 over U2. So you define a matrix like this of transfer functions. And if I multiply this matrix by the matrix of the inputs, what would you get? Yes, you will get Y1 and Y2. So here everything will be in matrix notation. Okay? In general, if you have N inputs or M inputs and P outputs, here both of them are 2. Then your transfer function matrix, if you call it G, your G is going to be what by what? Because this guy in general is P by 1, this is M by 1, so this is going to be P by M. Okay, you're going to have P times M transfer functions, okay? Now, what's the meaning of them? What's the meaning of each one? Let's look at the meaning. So what does this one mean? Or how do I find this one? This one means the ratio of y1 over u1 if we do not consider u2. So if I know u1, this tells me the contribution of u1 to y1. This tells me the contribution of u2 to y1. This is contribution of u1 to y2. This is contribution of u2 to 1, 2. So how do I find this? In order to find this, I set u2 to be what? 0. And then from the governing differential equations of the system, I solve for what? For y1 as a function of what? u1, and then I divide the ratio. The same thing for here. I still set what? u2 to be 0, and then solve for what? Solve for y2. Here I solve for y1. What about here? Since I'm interested in only contributions of u2, I set what? u1 to be 0, and then solve for what? Solve for y1. Here I set u1 to 0, but I solve for y2, okay? So in each column, you set any other input to 0. If there are 3 inputs, then let's say you have u1, u2, and u3. When you want to calculate the elements in the first row, you just consider u1. You set u2, u3, and as many other inputs as you have, all of them to 0. Okay? Only that guy that is in the denominator, you make that to be arbitrary inputs. The rest of them you set to 0. Okay? So this is how you find, and we'll go through examples. This is how you find the matrix of transfer functions for a multi-input, multi-output MIMO system. Now, in this course, we do not deal with MIMO systems. We only deal with SISO systems, but I might give you an example about how to find different transfer functions of MIMO system. The other important thing about transfer function is if the transfer function is unknown, you can find it experimentally. You can find it experimentally. You might say, why is it unknown? Well, because I cannot find the governing differential equation. This guy is not easy to find. Not all systems, it's easy to find their governing differential equations. They are probably too complicated to find their differential equation. Okay, they are like a black box. Then how would you find them? We'll see later when we go to frequency response, but basically what you do is, if the system is like a black box, so what you do, you pass to it a lot of inputs with different magnitudes and different frequencies, let's say different harmonics. So you give it like A1 sine of omega 1t, then you give it A2 times sine of omega 2t, and so on and so forth. So you change magnitudes. Mostly, more important than that, you change, even you don't need to have different A's, okay? You can just have different omegas. You don't need to change the magnitude really. So all you need is to change the frequency. So you give this, then you give this. So you keep changing your frequency, and in the output, you get basically here some B1 sine of omega 1t plus phi 1. So the magnitude will change and you get a phase shift. For the next one, you get B2 sine of omega 2t plus phi 2. the frequency of the output and input are the same, but the magnitudes are different and the phases are different. And here you get B3 sine of omega 3t plus phi 3. Okay, and so on and so forth. And then you'll create two plots. One of them is frequency omega, and here you have bi over a. So you divide each one of the output magnitudes by the input magnitude. You call it the this one, right? This is the magnitude of the transfer function. So you get a bunch of data here, and typically you do this in logarithmic or in decimal. We'll talk about that later. So you get the plot here. The other plot that you do is the phase, phi i's versus omega. And actually this one is in decibel, not the other one. This is in radians per second. And again, here you get some plots, right? And then this is also in radian. And based on these graphs, you can infer, based on these two graphs, you can infer what your g of s is going to look like. Okay, so if this g of s I don't know, based on these graphs, these frequency graphs, I can find or estimate g of s. Okay, this is a system identification process, and we'll talk about it when we go to the frequency response chapter. But the transfer function can be found experimentally if we don't know the governing DFQ. Okay, now let's talk about some important things. Now that we know transfer function, how we can find it, at least for an SISO system, we have gone through one example. Let's look at the meaning of some common transfer functions that you might see here and there. If the transfer function of a block is 1 over s, what does that mean? It means it is an integrator. It is an integrator, okay? So let me show you that. If you have a block like this, and input y goes in, u goes in, and input y comes out. And here, g of s is 1 over s. So y over u is g, and it's 1 over s. Therefore, sy of s is equal to u of s. Right? And you can add some extra y of 0 here, right? Because you know the initial condition is 0, so you can add some y of 0 here. You know that's 0 when we do Laplace transform of transfer functions, for transfer functions. So now if you take inverse Laplace, this is going to be what? Y dot, correct? dy of t over dt, and this is going to be u of t. So y, derivative of y is u, therefore y is what? Itself is integral of ut dt. Just multiply both sides by dt and integrate. So what is the system doing? It is integrating the inputs to give you what? The outputs, right? So this block is what? This block is an integrator, right? We saw in the previous example of the causal system that, where was that? Here. Or, no, actually here, I guess. More. Yeah, if it's s instead of 1 over s, then what does that mean? It means the input is derivative of output, right? So you're taking time derivative of input to get output, correct? So S means time derivative, 1 over S means opposite of that, time integrator. Now, if you have 1 over S squared means what? Double time integrator. If it's a rational function linear like this, A over S plus B, what does that mean? It means the output is the inputs passed through a low-pass filter. So if your input has noise in it, has high frequencies, then the output would look like input, but pass through a low-pass filter, right? So let me close some of this so that they get out of the way, because we opened up so many windows. And so as I said, if you have an input like this, a noisy signal, right? So this is U versus time. So your signal looks like this, right? When you pass it through a box, and that box is a constant A over S plus B. It's a low-pass filter. Then your output, if you plot it, would be the same signal but filtered out. So something like this, basically. Right? So it's the filtered version of this. The high frequencies would be filtered out. The opposite of that is if there is an S term in the numerator, then it's a high pass filter. So it will amplify your high frequencies and it will take away your low frequencies. If it's a general second order system like this, so you have a quadratic in denominator and a linear term in numerator, this is what we call a second order filter, okay? And we'll talk about this later when we get to, okay, now where can I find a low pass or high pass filter in real life? Which elements should I put together to make such a thing? So here I mentioned for you some examples, right? But when we get to our next chapter about modeling mechanical and electrical systems, I can show you that. Why is it that when you have a capacitor connected to a voltage source, it will integrate? If we have a mass and an external force, then the Laplace of the position of the mass over the input force, the external input force, is a double time integrator. And if you have basically, in no physical system can do S because it's not causal, but op-amps, you can create in op-amps operational amplifiers with transistors. You can approximately make this. If you have an RC circuit resistor capacitor with capacitor output, you can make low pass filter. If you put the resistor as the output, you can make high pass filter. And then a mass spring damper system or resistor, inductor, capacitor circuit can be, in general, a second order system, okay? So right now, just literally accept why each one of these is the kind of transfer function it is, but I can easily show you that. I can show you maybe this 1 over S squared right now, but we'll go over them in the next chapter. So let me just briefly go over that. That's fine. So if I have a mass, okay, and there is an external force F, and the mass is M, and the position of the block measured horizontally, this guy is X, And let's say for the moment this is frictionless, right? So if you draw the free body diagram of this block, what do you have? You have F, and then you have mg, and you have n. So if in the x direction you write your equation sum fx to be equal to mx double dot, right? X double dot is ax, correct? Second time derivative of x. Then the only force in the x direction you have is F is equal to mx double dot, right? And now you take Laplace. Remember that this, in general, this is f of t, okay? So this is f of t. This input force can be time variant. It's not necessarily always a constant force. So now I take Laplace from both sides of this. What happens? This becomes f of s. This one becomes m times what? S squared x of s minus x of 0 times s minus x dot at 0. And we know when we want a transfer function, we assume initial conditions are 0. Therefore, you only will be getting this term, right? And now if you find the transfer function of the output of the system, which is position of the part, over input of the system, which is the force, it is going to be 1 over m times 1 over s squared. Right? And let's say if m is 1, let's make life easy and say m is 1 kilogram, then this guy is 1, so you will get what? 1 over s squared, right? So you see a mass subjected to an external force, right? A mass of 1 kilogram. The transfer function of the system, output to be position and input to be force, is actually what? It is 1 over s squared. And it's not too hard to show the other ones too. Just to do a little bit more practice very fast, let me show you this first one too, since I mentioned the time integrator is a capacitor and a voltage source. So let me show you that as well. So here you have an electric circuit, you have a voltage source, and then you have a capacitor. So this voltage is V in time, and then the output of the system is the voltage across both sides of the capacitor, V out. So the goal is to find the transfer function of V out over V in, output over input, right? So what's the relation here? You know the governing equation for a capacitor is what? You all know that if this current going through the circuit is I, right? What relation exists between I, V, and C? So C, by definition, is Q over the voltage across both sides of this, right? Correct? So, 1 second. So this is going to be over V out. And then I can take a time derivative from this, or first I cross multiply, then take a time derivative. So Q is C times V out. Now I take a time derivative. Why? Because Q will be I, right? And then this is going to be C dV out over dt, assuming that C is constant, correct? And now what is I? How do I find I here? Correct? I need to find I, and how do I find I? Well, so One thing we need to change a little bit here, since I and V are related, but if V is constant, I is changing exponentially. So what I would like to do is, instead of calling it a voltage source, I would call it a current source. Okay, that makes life here, the modeling, easier. So let's instead use a current source. Right? That makes life easier for us. So this is I of t. And now from here, if you take now Laplace transform, this is going to be I of s. And this is going to be C times SV out of S minus V out at time 0. And again, initial condition is 0. And to make life easier, again, I assume C is 1. So this is 1. And from here, you would get what? You would get I of S to be S times V out of S. And therefore, your transfer function, which is the output over the input, it is going to be 1 over S, right? So the output voltage is the time integration of the input current, okay? So that's how. So what I would like to change here then, instead of voltage source, I would call it current source. Because if it's voltage source, then I have to add some more exponentials into it, and it's going to be a delayed version of that. So I'll talk about that later. I make it the current source to make life easier. Okay, so I showed you that case. Now, we have a couple of things to do, but before any of that, I would like to come back and talk about this example because I mentioned it. I felt so bad if I do not show you an example of that before I proceed. So I said if I have several inputs, several outputs, then I have a matrix. And then when I need to find each one of the terms in the matrix, I need to only use one input, and the rest of the inputs I set at 0. Right? So what does that mean? How do I do that here? Let me show you an example before I move any further. So let's go through one example together. And here, let's say I have a system like this, and let's make it a physical system. Maybe that can be something easier for you to grasp. So I have a block here with mass of 1 kilogram. I have a I have an external force F of t, and then there is a variable, a time varying friction here. And let me not call this F, let me call it something else, because I want to call friction F. So I call this maybe whatever U of t. And then this friction, which I can control the amount of it, I call it F of t. So both of these are input to the system. And then I need two outputs. One to be the position of the block, and the other one I want it to be the velocity of the block. X dot of t, right? So the system has two inputs and two outputs. And how do I find the matrix of the transfer function? Clearly here, my matrix G is going to be 2 by 2, right? Because I have two inputs, two outputs. Now, how do I find the block, the elements of that? So this guy here what elements does it have? The first one is going to be the first transfer function x of s over what? Over basically the first input u of s. The second one is first output over the second input. Then this is going to be v of s over u of s. And then v of s over f of s. Okay, so I need to find these guys. Now, first I write my governing equations. So here, I know the only other force I have is N involved and mg, but I'm only interested in the x direction. So if I write my forces in the x direction, it is going to be u minus f, right? This is equal to mx double dot, right? So that is the governing equation between u, f, and also is equal to mv dot, right? Because the time velocity derivative, the time derivative of velocity, first time derivative is acceleration. So I can use any of these to find what? To find my transfer functions. So now how do I do it? For the first element, I'm only interested in u. I do not care about f. So what do I do for the first one? I temporarily set this to 0 and say I do not care about this. And then from this 2, I solve for, and remember m is 1. I take Laplace of both sides of this, which is u equal x double dot, and then find what? The transfer function. So if I do that from here, I can see that u is going to be equal to x double dot and is equal to v dot, right? When f is 0 and m is 1. If I apply Laplace, what happens? I will get u of s is equal to s squared x of s and is equal to s times v of s. And remember that initial conditions, I assume v of 0 is 0, x of 0 is 0. Therefore, I can find x over u and I can find what? V over u. Right? So that's it. This guy is 1 over s. This guy is what? 1 over s squared. I found them. Now for the next column, I'll set what? I'll set u to 0 and I leave f. So I write it again. M is 1. This time I set u to 0 because I'm interested in f. And again, if you do that, your governing equations are negative f is equal to x double dot is equal to v dot. And if I take Laplace, I'll find that what? Negative f of s is equal to s squared x of s and is equal to s times v of s. And therefore, x of s over f of s is negative 1 over s squared. And then v of s over f of s is negative 1 over s. So I have these guys too. Okay, so now I got my transfer function matrix. Each entry of that is a rational function. Okay, so this was very simple example, but I just wanted you to know how to find the matrix transfer function of an Mimo system. Okay, so I guess now we know enough about transfer functions, and now it is time to learn a little bit more, a couple of things more, and then start talking about block diagrams and how to simplify them. So let's continue this lecture, right? This is where I'm getting into the second lecture, correct? So, wrong syllabus here. So we have covered this one. Now we are getting into this, right? And we'll finish this one. If time allows, we'll get into this one as well. If not, we'll finish it and then we'll go through this later. So let's see what happens. Okay, so another term we need to learn about the transfer function is characteristic polynomial. And what is this? It says the denominator of g of s, the denominator of a transfer function, is a polynomial, right? That polynomial, we call it characteristic polynomial. The roots of that characteristic polynomial, we call them what? Poles of the transfer function. Let me add one more thing. The roots of the numerator of a transfer function are called zeros of. Are called zeros of the transfer function. Okay, so I just wanted you to know that. So the definition of pole, the definition of zero, and then the characteristic polynomial. I just want to make sure everybody knows that, right? Now, we'll talk about it and I'll show you later. If you want your system to be stable, the response of the system to some input to be stable, stable means what? Means the output does not grow unbounded, does not go to infinity, and converges to a constant value, then the poles of the transfer function have to be what? Have to have negative real parts, or they have to stay on the left side of the imaginary axis. Okay, that is very important. So let's talk about all of this. Okay, so for example, the previous transfer function that we derived, if you remember, it was like s plus 1 divided by s squared plus 2s plus 3. Okay, so that was a transfer function. Now, let's learn about several things. One is the order of the transfer function, which is the highest order of polynomial of the denominator. So this 2, the highest order of polynomial, this is the order of the transfer function. We say order of g of s is equal to 2. Then this polynomial in the numerator, if it has any root, so we set this equal to 0, any root we find, which is just -1, we say this guy is what? This is 0 of the transfer function. Then we set the denominator equal to 0. And whatever we find, which in this case they are two basically complex numbers, right? -1 plus minus 2 square root 2. So it is going to be -1 plus and minus a square root 2 times j. J to be the root of the complex numbers. Okay, so these two are the poles of the transfer function. Then this polynomial itself in the denominator, this one. This is what? This is, the characteristic polynomial of g of s. Okay, so the denominator is polynomial, the polynomial from which we find the poles of the transfer function. We say that is the characteristic polynomial. Why? What does characteristic mean? Characteristic means it determines the behavior of the g of s. Why? Because the roots of this are the poles, and poles will determine whether the system is stable or not. So in this case, if you look at the poles, the real part is negative and their imaginary part is positive negative. They are complex conjugates. So if you plot these poles in the complex plane, right? So this is the imaginary axis and this is the real axis. These poles are like here. One of them is here, one of them is here. Correct? Where this is -1, this is a square root 2, this is negative square root 2. And since these poles are on the left side of the imaginary axis, so as long as my poles are here to the left of the imaginary axis, this tells me that my system is what? Stable. If they are on the right side of the imaginary axis, which I'll show you in the next example, the system is unstable. And if they are at the imaginary axis or on the imaginary axis, then we say the system is, we'll talk about this more in the next chapter, but we say the system is marginally stable. Now, what does that mean really? When we say stable, unstable, what does it mean? It means to this system, if we provide an input, let's say just a constant input, 1, we make sure the input of the system is just 1 unit. How does the output behave? Okay, right? So to this system, this transfer function is what? Output Laplace over input Laplace. So if I give the input to the system of 1 unit, right? So this is u, this is y. Let's say I just make u to be 1 unit. What is y? Right? If I do a constant push of 1 unit on this mass, how does the position look like? Okay, and we'll see that later, but I'll show you right now with Matlab just to have a better understanding. So I'll define this transfer function. I'll provide a unit step function, right? Because if you remember, the step function is the function that before time of 0 is 0, after time of 0 is 1. So I provide a unit step function to that system with this transfer function, and then I want to look at the outputs. So as we'll see later, the way to define a transfer function is we use the command tf. So no worries, I'm going ahead, but that's fine. And here I provide the coefficients of the numerator, 1 and 1, and then the denominator, 1, 2, and 3. It makes a transfer function for me. And then when I say command step of the transfer function, it shows the response to a step unit step input. So look at this behavior. And you'll see stability, right? So look at here. What do you see? I provided an input of 1 unit, and as you see, my output starting from 0 is growing to some number, then it is going back and ultimately settling at this constant number here, right? Which is about 1/3, or exactly 1/3. So my output does not grow unbounded. Even if I plot this for more time, instead of 6 seconds, I plot it for a lot more time, then I can still see that the output is not going to go unbounded. It is going to converge at a finite number and stays there. So we say this kind of behavior is what? Stable. The position goes to the final number, oscillates a little bit about it, and then the oscillation goes away. This is this underdamped behavior that I mentioned in the past, okay? So if I want, I can definitely get more, right? So you can provide time, correct? And then find the answer for so much of time. So let me make it to plot for a little bit longer. So I go from 0 to, let's say, 100 seconds. And then I say step of G and T. And there we go. You can see this is the step response for 100 seconds. So I go up, I have some oscillation, and then what? I settle at the constant number and I never grow unbounded. Yes? Now, if on the other hand, you can see the roots of the denominator, right? The roots of 1, 2, and 3 are those two things that we found. -1 plus minus a square root 2, right? These guys. They are on the left side of the imaginary axis, so the behavior is what? I converge at a constant number and stay there. Now, if we make it unstable, so what do we need? We need this -1, let's say, to go to +1, okay? If they are on the right-hand side, then my behavior should be completely different. For example, if I just make this +2, -2, okay? So my transfer function is like that. Now, the roots of the denominator, if you look at them, the poles, they have what? They have +1, so they are on the right-hand side, right? So now look at the behavior this time. The only thing I changed is the signs of the real parts of the poles. They are on the right-hand side of imaginary axis now. I still want the step behavior. Now look. You see that? Look at the number. It is going up, and then look at this. Look at the order of this number. How much is it? Yes, 10 to the 42. It is growing unbounded. Even if I plot it for 10 seconds, you might see that as well. You don't need to go 100 seconds in this case because it is growing so badly. Look at that. Just in 10 seconds, I am at what? 25,000. Right? And as time goes, this one goes up, and you see at 100 seconds, it was 10 to the 42. So it is growing exponentially, and ultimately unbounded, goes to infinity. So a physical system like this cannot stand, right? Imagine the input is the force and the output is the position of the mass. What does it mean when the position of the mass is 10 to the 42? Can a physical system move that much? No. It goes unstable and will ultimately collapses. Right? It destroys itself. So unstable systems, they cannot sustain their behavior. They will ultimately explode, collapse. Stable systems, no, they have no problem, right? Another example that I can give you about stability, because it's important, although we talk about it later, but I want you to know a little bit about this topic, is if you have a ball, and this ball is on these two surfaces, convex and concave. If you have a ball here at the bottom of this concave surface, if you give this ball a little bit push, what happens? So bring it up here, and then let it go. What happens? Yes, it comes down and keeps oscillating. And because of friction, the oscillation will wear out and ultimately go back where? Where you started. You will settle there. So your position does not grow unbounded. You go back to a constant position. So this is stable, right? Now what about this case? If you put the ball here and give it a little bit push and bring it here and let it go, what happens? Yes, it will never come back. It just keeps what? Keeps going further and further away, right? So this is what? This is unstable, right? The same can be said about the pendulum. If you have a pendulum, a regular pendulum, normal pendulum, correct? So that is your pendulum. If you move it a little bit away from the vertical position and let it go, what happens? It keeps oscillating and then settles, right? At the vertical position due to friction. But if it's an inverted pendulum, so you did a lot of work and could make it stay upright. Now if you give it a small tilt and bring it here, even if it's a fraction of a degree, what happens? It just keeps going. It never comes back. So this is unstable, this is stable. Okay, that's the same thing for physical systems. Whether the output grows unbounded or it keeps going back to either the initial position or something constant, which is finite. So stability, instability, and we can tell this behavior just by looking at what? Just by looking at where the poles of the transfer function are. If the poles of the transfer function are on the left side of imaginary axis, the system will show stability. If they are on the right side, they are unstable. Now, what about if they are exactly on what? On the imaginary axis. So they do not have a real part. They are just like positive and negative to the square root 2j. That's it, right? So in this case, all I need to change is this transfer function, right? I want them at basically this. If you look at this, the poles of the denominator are at plus and minus a square root 2j. So they are exactly on the imaginary axis, right? Now let's look at the behavior of this system. What do you see? Let's make time bigger. What is it? It's sustained oscillation. The output will never set at a fixed value and also never grow what? Unbounded. It just oscillates between two numbers. It's sustained oscillation. So we don't call it stable, we don't call it unstable. We call it marginally stable or marginally unstable. Okay? So marginally stable means what? Or unstable? Means sustained oscillation. So now we know why we call the denominator of the transfer function characteristic, because the roots of that, or the poles, will tell you everything. Will tell you how the system would behave. Okay, so in the case of this system, as I just showed you, the denominator has two roots, two poles with real parts that are positive, and so this system will behave what? Unstable. Okay, so these are some of the meaning, right? So I say if it's stable, if it's unstable, right? Now let me add that again, since I mentioned it, I want your notes to be complete, although stability, we talk about it in more detail in the next chapter, but I want you to have everything at hand. Okay, not grow unbounded, these poles have to be. If the poles are on the right side of the imaginary axis, the system is unstable and the output will grow unbounded or exponentially if the poles are on the imaginary axis. Then the system is marginally stable and the output has sustained oscillations. Okay, so that is important. Now, let me mention something that probably crossed your mind, and that is what if some of the roots are on the left side and some of them are on the right side? What about then? It doesn't matter that you have one root on the one pole on the right hand side of imaginary axis or 10. One is enough to make the system what? Unstable. So for the system to be stable, all these poles have to be on the left hand side. If even one of these poles, even one, is on the right hand side, the system is unstable. And if even one of the poles, of course you never have one of the poles, the roots are always complex conjugate, so it's always going to be a pair of the poles. So even one or a pair of the poles is or are on the imaginary axis, then we say the system is what? Marginally stable. So one is enough for marginal stability or instability, okay? If you want pure stability, everything should be on the left side. So please keep that in mind. Let me make it bigger for you. There we go. Okay, fine. One other thing we have to talk about is impulse response. So the transfer function of a system is the time version of that, okay? The inverse of the transfer function, the g of t, not g of s. We call it the impulse response of the system y. So if we apply inverse Laplace to the transfer function g, then g in the t domain, we call it impulse response of the system. Why is that? Well, assume that you have a physical system and you send in an input where this input is the impulse function delta of t, delta of t. Last time we called it delta or Kronecker delta. That's also called impulse function. And the output we want to find out, and the transfer function is g of s. Okay, so the input is delta or impulse function, the output is unknown, and the transfer function is g of s. So what happens? Well, we say y of s over u of s is equal to g of s. Therefore, y is u times g. But if you remember, what is the Laplace of delta of t? Yes, if you remember, this is 1. Laplace of the delta function is 1, right? Just go back to your slides. And if you go back up here, that's the first property, right? The impulse function Laplace is 1. So that is 1. So y of s is the same as what? U of s. So if you take inverse Laplace, what happens? Y of t is going to be the same as what? G of t. So the output or the response to the impulse function is also equal to what? G of t. So that's why we call G of t impulse response, right? Response or output. Response is the same as output to an impulse input, right? So if somebody says, what is the impulse response of the system with this G of s, you just invert that G of s and then find what? The impulse response, right? So let's say in the case of this one here, if somebody says, what is the impulse response of this system? So you use the command I Laplace or you use partial fraction expansion and find it, right? Which you can see just basically from here, it is a combination of sine and cosine. But if you want to do that, use the symbolics, correct? And then define G. Let me use another letter because I used G already unless I do clear G. Then say G is equal to s plus 1 divided by s squared plus 2. And then I say, what is I Laplace of G? Right? And then I can make the answer to be pretty. So this function here, cosine of square root 2t plus a square root 2 over 2 sine of square root 2t. This is the impulse response of the system. So if you give the system an impulse input, that is how the system behaves. And you might wonder, what does impulse mean in physical word? It means a shock. Okay, so if this is a car, if this is an object, a mass, a car, anything, with that transfer function. So it's a car. And that G of t that you had, which was cosine of square root 2t plus square root 2 over 2 sine of square root 2t, what does that mean? It means the position of this object, if you call it x of t, the output, and the input to the system, a force F of t, if you make this F of t to be delta t, what does it mean? It means somebody come here and then what? Give it a push, a sudden push, not a continuous push, just a shock. So you basically hit it. You give it a sudden shock and then pull back your hands, right? Just a shock. How does the position of this car would look like? Well, it looks oscillatory. So if you look at this car, and probably you have seen that, right? If something is, a car is there and the brakes are applied and you give it some sudden hit, what do you see? You see this car goes like this, a little bit oscillates. Now this is sustained oscillation, which is not typical because there is a lot of friction. So in real life, you will have some extra term here, like a negative exponential term or something like that. And that negative exponential makes this oscillation to what? To fade away, and then the car stops, right? So it behaves like this, under damp, correct? Now, this means it keeps oscillating, but in real world, that's not the case. And the reason is because the denominator of that transfer function has some extra term. It's not just as simple as s squared plus 2. There is an extra term, right? So your transfer function looks like this, plus 2s plus 3. And so this is your transfer function. Look at that. Exponential of negative t cosine of that, right? So you have this one. So when you plot it, it will ultimately damp out and go to 0, right? So the response of the system to a sudden shock, a sudden push that is not continued, that is how it would look like, okay? So I hope I could clarify the physical meaning of impulse response. Good. Now you can also find it using convolution, but I don't want to get into convolution integral because we barely use it in this course, so this part you can just neglect it. Fine. So now I think I know enough with you about transfer functions. Now, block diagrams. So block diagrams is a way to visualize the behavior of a complicated system. Not all systems have one single block. It's not like they have one single component for which you know the relation between input and outputs. Most of the systems have so many components, and each component has a block for itself. Each component has a relation between input and output. Okay, so if you have a signal like X, this X can go inside the block, can come outside the block, right? Then output of the block is input times the transfer function. Sometimes you have to add and subtract some signals together, right? Remember in the first lecture when we had desired output minus actual output, we subtracted and we got error, right? So we subtracted two signals. So sometimes we have a what? A summer block, and where the output is input 1 plus input 2 or minus, or there could be several inputs added or subtracted. And sometimes we have a what? A takeoff point or a feedback. So from this output, we get the feedback through a sensor and send it back to the system. So we have what we call a takeoff or a branch. You might also call it the branch point. Or feedback point. You have summers, you have blocks, and you have simple signals, right? So all of this can happen in a physical system. Like what? Like a speed controller system. Let's see how we can present the system, the physical system, using this method of block diagram, right? Where you replace each portion of the system with a block or summer or branches, and you visualize how the system is behaving, right? So let's talk about this. So what do I have here? So this is a system that is going to control the RPM, the angular velocity of a load. So what you do here is you, through a potentiometer, a pot, will set the RPM at which you want this load, which is rotated by the motor, to spin, okay? Let's say I want this load to spin at 2000 RPM or 1000 RPM, right? Anything that you want. Let's say it's a drill bit, it's a Tremel, it's a load in the engine, whatever. So you want it to go at 2000 RPM, but right now it is not. It is just rotating 1500 RPM. So what does the system do? It measures the RPM of the actual load using this sensor called a tachometer. And a tachometer will measure the RPM, convert it into voltage, and then this potentiometer also converts the angle through which you rotated it to a voltage. So the two voltages come to a summing block, a comparator, what we call it, and subtracted. The difference between them is called what? The error in voltage. Now, since typically this voltage error is small, it is not enough to turn the DC motor, okay? Or it's not sufficient for the armature current to provide an armature current for the motor to spin faster or slower. Typically, that's not enough. So we amplify it using transistors. We multiply this voltage by a constant K1, which is typically way bigger than 1. And we make amplified voltage VC. Okay? Yes? And then we multiply it one more time here by this power amplifier. And we make it VM. Okay? So we need an external power to give it more power so that it can create amperes, right? We know what creates the torque on the rotor of a DC motor is electric current. The torque that is generated on this shaft is proportional to this electric current. So in order to get more torque, we need what? More current. And voltage by itself cannot just provide a lot of current. We use the external power source so that we can draw some good amps out of this external power source. So now, through this circuit of the armature here, or the rotor, which has a resistance and an inductance, will generate a current. Then the torque is a constant, we call it torque constant, KT, times the current. Then this torque will be applied on this gear speed reduction system and then applied to the load. Okay? Yes? And so there is a disturbance of T of load that can be applied. Okay, so let's say what? Let's say you're drilling something. So this guy is the drill bit, but depending on what you are drilling, you will get an opposite torque, right? Because you are drilling something, so you will get some negative torque on your way. So this external torque from the load, it is like a disturbance to the shaft. Okay, and then it comes in, and then the summation of the two, or subtraction of the two, with the electric motor torque positive and with the disturbance torque negative, will go into the shaft. And in the shaft you have an inertia and you have a viscous friction element, okay, or a rotational damper due to lubrication of the shafts with lubricant. That will generate an RPM for you if you integrate it, and then that RPM is multiplied by the gear reduction to give you omega of the load. So omega here is the angular velocity, and you know the RPM of the shaft and the RPM of the load are not the same because there is a gear here. So N here is the speed ratio, the gear pair, right? So for example, if this one has, let's say, 8 teeth and this one has 24 teeth, so this one is rotating 3 times faster than that, so N is 3 here. So your RPM drops by 1/3, so N is going to be like 3, okay? Also, the tachometer itself has a gain, so when it converts the RPM to voltage, it has a gain, so the voltage is proportional to the RPM, and that's what happens, right? And here also, the RPM that you want, you insert it by turning the pot. So there is a dial gain to give you an angle, and then the angle proportional to that will be a gain that will give you a voltage. Okay, so the product of these two, we call it gain K of the pot, actually. So it's K of tachometer. And we set them to be equal to K of tachometer because we want these two angles to be subtracted from the same thing multiplied by the same gain. Okay, it's more complicated than that, and I don't really know how much you guys remember from electric circuits, but we'll go more through this as we go further through this course. But you can see that the behavior of each one of these elements, physical elements, is shown here. Whether you're subtracting something in the comparator, whether you're multiplying, you show it by a constant gain. Whether it's an input-output relation, you show it by these transfer functions. Whether it's simple gain because of gear reduction, you show it by 1 over n, and so on and so forth. And whether you're getting a feedback, that you're showing it here. So this block diagram shows the behavior of that system, right? Good. So now we get to reducing block diagrams, but before that, I want to at least draw or mention one more block diagram so that you can familiarize yourself with this idea before I talk about how to simplify them and reduce them to a single case. But the example I think would be nice for you is the drive system of an engine. By the way, this site, how stuff works, once in a while, take a look at this website. It's an amazing website. You can learn a ton of things from this guy. So let's say here, if I'll come and talk about here, so in a typical car, the input to your system is engine and the amount of accelerator angle that you provide, right? So you push on the accelerator, and the angle of the accelerator would determine basically whether you want to or how much you want to change the speed, right? It determines the acceleration, and then that push will determine the amount of fuel that goes to engine, so that will determine how fast the engine rotates. That RPM goes to a gearbox, comes out of gearbox different, then goes to the drive shaft, goes to the differential if it's rear drive, and then in the differential, the direction of rotation is rotated 90 degrees and goes to the tires, and then that RPM is multiplied by the radius of the tires to give you what? To give you basically the speed of each tire, and then based on the difference and the average of the speed of these two tires, you can determine how fast your car moves forwards and how fast it spins about its centroid. Okay, so if I want to show a block diagram for a typical car system and I consider it the differential drive with only rear differential, I can draw something for you here. Okay, so there are two inputs that you have, or three inputs actually you have in a car. So you have accelerator, you have brakes, and you also have the steering. Okay, and let's say for the moment I don't care about the steering, I only care about the velocity of the car. So the two inputs are accelerator and brake angle, and the output is what? Just velocity of the centroid of the car. Okay, so for the moment, let's just put aside the steering and the yaw angle of the car. Okay, it's a little more complicated. So what you have here is basically you have your engine, and then inside the engine there is a transfer function, okay, like G1, where you provide basically the angle of the accelerator as the input. But the thing is, the angle of the accelerator is not directly going to the engine, it is transferred through a mechanism, whether mechanical or electrical, into the amount of fuel that goes into the engine. Okay, so here comes fuel, but that fuel is determined by what? by the position of the accelerator, right? So this is the accelerator's position. It goes into a mechanism, right? G2 of S, or if you want, you can call this one G1 of S, the other one G2 of S. So through that mechanism, you will get a command to your injectors, correct? And then the injectors will determine how much fuel is flowing into your engine. So there is injectors here as well. So if you wanted really with detail, let's add detail. So this is injector G2 of S. Okay, and this is fuel flow rate, the amount of fuel that goes into the engine per time. Okay, and then comes out of engine and RPM. Okay, so it is going to be RPM or omega, this is G3, of the crankshaft. Okay, so this is the RPM of the crankshaft, which goes out. And then that is going to go inside your transmission. So let's say your transmission has G4 of S. And then transmission will have a transfer function. It could be as simple as a gain, so it make the RPM go up or down, but it's not really that simple. But if you consider it a simple, very simple manual transmission and neglect the effect of lubricant and friction and everything, you can just consider it a gain. Then this one goes into what? This one goes to the drive shaft, and then it goes to the differential. Differential also has a transfer function. Okay, again, it could be a reduction, which it is actually, and some more effects of friction, but if we just consider it G5, so we are not going to talk about them exactly what they are because they are quite complicated. So this is omega of the drive shaft. It goes to differential, and then differential has two outputs. One output is omega of the right tire or right axle. One is omega of the left axle. Then these omegas, I can say they are multiplied by the radius of the right tire and the radius of the left tire. Very simple again, in order to give you velocity of the left tire or wheel and velocity of the right wheel. And then the average of these two, assuming that there is no slip, the average of these two, so this is a summer block, multiplied by a gain of 1/2, it is going to give you what? The velocity of the car centroid. right? So this is, as you can see, it is quite complicated. And that is one thing. But actually it is more complicated because here I'm just showing you accelerator and velocity of the car. So what about the brake? So you also have the brake, right? So you have the brake mechanism. And this one is going to be the brake pedal. Angular position. Right? And this is its own, again, mechanism. You might call it G6. It converted into a voltage through the brake mechanism, and that will apply a torque on these tires to generate omega. So these omegas are not that simple, okay? Indeed, these brakes that are coming on the left and right should go and be added to the torque that is coming out of the differential, and then through some transfer functions you can have omega of left and right. So if I want to do it a little better for you, I have to do something here in between. So I have to bring this guy here and this one. This is torque of the differential. This is torque of the brake, right? And subtract them. And then take them to two transfer functions, which takes torque in and then speed out the omegas, right? So I might call this G6, I might call this G7. Then this one will give you omega of the right, and this one will give you omega of the left. Okay? Again, it's even more complicated than this. So this is just the feedforward system, brake and accelerator. Now if you have a cruise control, the cruise control will get a feedback from here. Okay, it will get a feedback from here. And then you have your own what? You have your own speed. So you told it what speed to go, so desired speed. And then it gets the feedback from this guy, the actual speed. So you have a sensor here, you have to have a sensor that will give you actual speed. So here you have a way to measure the speed of the car, and you really do not measure the speed of the car. What you really sense is these omegas. Or you divide that, okay, you divide that V by omega, or you, as I said, you really get these two omegas. You get your feedback from these two omegas, okay, using tachometers. And then multiply them by 1/2 times R. So you need, if you want it really good, let me do it really good for you. So you get feedback from here and here. Okay, so you get the feedback here, you get the feedback here using tachometers. So that here you have omega of the left measured, here you have omega of the right measured, right? Then you multiply each one of them by those gains, radius of left, radius of right. Then you add them together, and multiply by 1/2. And that is going to be the estimation of the car from the speed. If it has a GPS, then it might directly get it from GPS. So then the difference between these, which is the error speed, will go to what? Will determine how much the brake should be pushed, and it will determine how much the accelerator will be pushed. Yes? So, yes. In real life, in engineering, the block diagrams are quite complicated. And finding each one of these transfer functions is hard. Many of them are not even linear. So the transfer functions are actually approximate. They are not accurate. Okay, so let's continue about reducing block diagrams and simplifying them and finishing this whole chapter up if we can. So how can we simplify block diagrams? So if you have a big thing like this, is there any way that I can replace all of these blocks, summation points, feedback, and everything with one single transfer function, like here, that can directly relate my input to the output? So omega sub r comes in and omega L goes out. And I call that G of S. How can I have one single block that can replace all of that? That's called reducing or simplifying the block diagrams, right? It's way easier to deal with one function, although this is going to be complicated itself, but it's just going to be a numerator and a denominator and a lot of parameters in it instead of all these wires and branches and summers and everything. So that's the goal. Now, how do we do that? There are some rules that if we follow, we can simplify any complicated system. One, if there are two blocks in series right after each other, then you can simply multiply them, right? Because here x over b is t2, b over f is t1. So if you multiply, you can see that x over f is t1 times t2. If there are two blocks in parallel, then you simply add them together. If there is a feedback loop, then in the feed-forward direction, you have G. In the feedback direction, you have H. Then the closed-loop transfer function, x over f, is going to be G over 1 plus or minus G times H. If this is a minus, you will have a plus. If this is a plus, you will have a minus, and I'll show you right now why. Okay? So again, G is called feed-forward transfer function. We'll talk about that later. H is the feedback one, and then x over f, we call it closed-loop transfer function. So why is that? So let me show you that. At least one of them I'll show you where that comes from. You don't want to just memorize stuff. So again, I said if it's negative here, it's positive here. If it's positive, and both signals are added, then here is negative. They are opposite of each other signs. Why is that? So I'll show you the case of this negative and that positive. Why? So if you look here, x here is g times a, right? So x is g times a, but what is a itself? A is f minus b, and what is b? B is x, because that's x, times h. So from this two, a is what? A is f minus x times h. And then if you plug that up here, then x is g times that, so it's gf minus gxf. gh, sorry. Yes? And now if you take this gh to this side, you will get x times 1 plus g h is equal to g times f. And therefore, the outputs over inputs Laplace, x over f, this guy here, if you call it g prime, this g prime from this top one is going to be what? G over 1 plus G H, okay, which is this guy. Now I can easily show that if this is a plus here, then this is going to be a plus, so here is going to be a minus. Okay, it's not hard to show. So simplifying blocks in series, blocks in parallel, and feedback loops. Okay, these are quite reasonable and easy to understand. Now, a couple of more things. These are a little higher level, but sometimes we might need them. Like what? Sometimes you want to move a summing point, a summation point, behind a block or ahead of a block. What does that mean? So here you see this summing point here is to the left or behind G. Now what if I move it to after G? It says fine, you can move it to after G, but then whatever that was coming here, as a feedback, excuse me, you have to multiply it by G. So you have to add this G block to the feedback loop to have the same behavior of the previous system. On the other hand, if you move it from right to left or from ahead to before, then to the feedback you have to add reciprocal of G to have the same behavior. Why is that? So let me show you that one as well. At least one of them. So moving a summation point, and then next one is moving a branch point. So I just want you to see them without just accepting them from me just because I say so. Never do that in my classes. Always ask for a reason, a proof or something, okay? Not in my class, in any other class. Always ask for a reason. So here we go. Why are these two equivalent? Well, if I call here this signal, whatever you want, A, and this signal B, what is the output here? So this is going to be A minus B, correct? And this is G times that, so it is going to be G times A minus B, right? So the signal going out is G times A minus B. But look at here. This is still A, and this is still B. Here, because I moved the summation point from before to after, only A is multiplied by G. So this is AG. So if I don't add this guy here, what would you get at the output? You would get AG minus B. If I don't add this purple block, you will get AG minus B, while here is what? AG minus BG. So in order to have that B times G, I will artificially add the G here so that now this is the same as the previous one. Yes? You see? Because again, I'm moving this from left to right. Now not both signals are multiplied by G. Only one of them does. So the other one that does not, I have to artificially add that block to make them equivalent. Why should we do that? I'll show you. Sometimes moving a branch point or a summation point from left to right of a block will be the only way to simplify it. And I'll show you why. Now, conversely, if you move a branch point from behind a block to after a block, then the feedback that you get from the branch should be multiplied by reciprocal of the block. If you move it from after to before or ahead to behind, then you would multiply it by the block. Okay, so let me show you this one as well. Why? So the rule for summation is exactly opposite of this. Right here you go from left to right or behind to ahead. you do the signal coming, the feedback signal coming by G. Here you do what? The outgoing one by 1 over G. So let me show you that also. So here the signal going is A, and before it goes to G and becomes A times G, I get a feedback. So the signal going out is A. But here A goes, and before I get the feedback, it's already multiplied by G. But I want A out. If I don't have this, I will get A times G out. If I do not add that 1 over G, then I will directly get AG, which is different from A. But when I multiply it by 1 over G, then I would get what? A out, right? So if I want to get the same out, the same feedback, I need to have this 1 over G artificially added. And opposite of that when I move it from right to left. Now, if you have two adjacent summation points, you can swap them. Okay, if you have two adjacent summation points, you can swap them. If you have two adjacent feedbacks, you can also swap them. As long as, you keep the same branch, it's not going to affect anything. So here it doesn't matter whether you first add these two, then, or subtract these two, then subtract these two, and then add everything together, or reverse it. So swapping adjacent summation points is not going to change anything, or branch points, right? Okay. Now, here, before we get into examples and relevant MATLAB commands, I want with you to know three terminologies which are important. One, in this feedback loop here, we call G, which is directly between output and this error signal, this G only, we call it feed-forward transfer function. The transfer function between the feedback B and what? The error A. B over A, okay? Which does not have anything to do with the actual input of the system. This one, we call it open loop transfer function, and you can easily show that it's the product of the feedforward G and the feedback H. So if you multiply feedforward G by feedback H, G times H, we call it open loop transfer function. And finally, closed loop, which is X over F, we just showed that it is G over 1 plus G H. Okay, I don't know why is this a bigger font. Yes. So I guess we proved that, but just want to make sure you all know that. So feed forward H, we can also call it feedback transfer function, right? It is feedback transfer function. If we want, we can add that, but it's obvious. Feed forward, feedback, open loop and closed loop transfer functions. Let me add that since I mentioned it. I always feel bad that my lecture notes are incomplete. Okay? Yes? And there are sometimes some acronyms for them. So this is called FFTF, feed forward, right? This is open loop transfer function, OLTF, and this is what? Closed loop transfer function, right? And this is just feedback transfer function, FTF. So just want you to know everything that you should know. Okay, so now let's see how we can do examples and simplify things, right? So there are several examples and things you can do. First, let's actually do this one. And relevant Matlab commands. I'll show you how to use relevant Matlab commands to confirm your solution. And then we do this one, which is a little bit more complicated. Okay. So in Matlab, if you want to form a transfer function when you have the numerator and denominator, all you need to do is to pass the numerator coefficients of polynomial from the highest to the lowest, and then the denominator. Okay, so you can have that command tf to create a transfer function. If you have two transfer functions, G1 and G2, or system 1 and system 2, then command series, consider them to be what? Like this. So the result will be the product of the two. The command feedback, consider them to be like this third case. So it gives you G over 1 plus GH, and G and H are system 1 and system 2 in this command. And if you say parallel, it just adds them together. Okay, so we have the commands TF, series, feedback, and parallel. And using these guys, we can also let Matlab take care of the simplifications for us. So let's look at this example together. And we also, you can see I have added for you the relevant commands, but I'll do it for you here. So how can I simplify this? On the paper and then using Matlab's help. So somebody gave me this and say, you replace this for me with a single block where you send in U and it gives out Y. If you call that G of S, what is that G of S? So the system, two systems are equivalent. Well, how do we do that? So we'll try to use those rules. Basically, parallel blocks, series blocks, feedback loops, swapping the summation point locations, the branch or feedback points, and then swapping just the summations together. So if you look here, the simplest thing I have, and you always start from the inner of the whole thing and goes toward the outside. So if you look here, this guy is a feedback loop where this is F and this is what? And G, right? This is F and this is H, whatever you want to call it. So you can replace that whole thing with one single what? With one single block, which is what? F over 1 plus F H. Why plus? Because this is what? Minus. So if I replace that and simplify, what do I get? I would get 1 over S squared plus 3s plus 2 divided by 1 plus that same thing multiplied by 3. Yes, and if you simplify, what would happen? This 3 comes here, and in the denominator, use a common denominator, so you would get this, and then 1 will be multiplied by that, and then this is just going to be 3. So if you simplify, your simplification is 1 over S squared, right? These two will go away, over 3s plus 5. So this is the simplified version of that whole thing. So I can say now, I can redraw my FBD, not FBD, sorry, the transfer function to be like that. So this is 7. This whole thing is just one block like that, goes out to be y. Y comes back with a 1 over s, comes here. And this is 1 over s squared plus 3s, right, plus 5. So I have simplified it. I come from here to here. Now what? Yes, now if you look, these two blocks, these two, are in series. So I can replace both of them with a what? With a product of the two, right? So what I can do now is I replace them with one single block, and here is another single block, and this guy is y, and this is 7 over s squared plus 3s plus 5. And again, if you look at this, this is just one single feedback loop, right? Again, you can call this f, and you can call this h, and you can simplify that to one single big block, where that single big block is f over 1 plus f times h, again plus because here is minus. So again, you replace what you have. And again, you take common denominator. So in the denominator, you have both of these terms multiplied. And here you have s squared plus 3s plus 5 plus 7 times s, of course. Okay, and when you simplify, you will get 7s, this s goes up, and here you get s cubed plus 3s squared plus 5s plus what? 7. So that guy here is your simplest that you can get. So that is how you simplify it, step by step. Now, in Matlab, you can do a similar thing. First, you create a transfer function for this block. You say the coefficient of the numerator array is 1 because there is only 1. In denominator, if you sort it from the highest order to the lowest order and look at the coefficients, you have a 1, you have a 3, and a 2. So you use that. So when you do it, system 1 will be this guy here, right? So look. First, I make this transfer function, just like that. Now I say that with this block, which is just 3 and 1, right? The numerator is 3, the denominator is 1, 3 over 1. That's system 2. So system 2 is just this gain 3. It is what? It's a static gain of 3. Now I say system 1 and system 2 are what? In a feedback. And the result of that is what? System 3. So system 3 is when you replace this whole feedback loop with one transfer function. Correct? So that is 1 over s squared plus 3s plus 5, what we just found here, if you remember. Here. Then we say that guy with 7. So 7, we call it a system 4, 7 and 1. And then you say that one and system 3, the one that you got from feedback, are what? In series. So multiply them together. Right? So system 4 is just again 7. Multiply them together. So this is the result series. Correct? Which we had over here. And now that one and this system of 1 over s are in a feedback. How do you define 1 over s? So 1 over s, in the numerator you only have 1. In denominator is 1 times s plus 0 constant. So you have to say 1 and 0. So the system 6 is just going to be the integrator. You see? 1s plus 0 constant. And then you say the final answer is what? Is going to be feedback between 5 and 6. And that is what I found at the end. Okay, so you can use Matlab to just confirm your simplifications. When you did all of the simplifications here, you can make sure that your results are correct by using some relevant Matlab commands. Okay, so we learn about that. There is one more thing here that is interesting to see, because here you see I have not just provided a numerator and a denominator, I did a little bit more than that. What does that mean? Let me just show you. What is this? What does that mean? It says 1 and 1 in a bracket, semicolon 1, then everything in braces. Then in another brace, you have 1, 2, 2, semicolon 1, 0. So what is that? It means here, this is to define a multi-input, multi-output transfer function matrix. You say the numerator for the first transfer function is 1 and 1. And the denominator of that is what? 1, 2, 2. The second transfer function, which is between the second input and the only output, is numerator is 1 and denominator is what? 1 and 0, right? So using braces and then putting the vectors or brackets inside them, we are able to define a matrix of transfer functions. So if you need to define an MIMO system, you can use this. But again, we don't do MIMO system in this course, but just wanted you to know about that, okay? So here I have defined this slide for you and added some more text to it. And here, instead of just some numbers, I put two general variables, a and b. That tells you these are the numerator and denominator vectors for the coefficients of the polynomials when you sort it from the highest order to the lowest order, and here to define an MIMO transfer function matrix. So I just added these explanations for you. Now, finally, let's go through this example, which is another interesting example. So here your system has two inputs and one output, and the problem asks you to find the transfer function for x over f and then x over g, because f and g are inputs, x is output. Okay, and you have to turn them into the simplest form possible, right? So you have to do a reduction. So let's do that. So when, as I said, when it says what is x over f, it means g is neglected. Okay, so first we want to find x over f. When we want to find this, we assume that every other input other than f is what? 0. If that's 0, means we don't have this here. This is going to go away. And so this branch point. So it is going to be just a straight line like this. Okay, which makes life quite easier for me. And I don't even need that. So how do I do it? Well, here these two 1 over s's are in series. So I can simplify them to be 1 over s squared. Then that 1 over s squared and the 3 are what? Are in a feedback. So this whole thing, if I want to simplify it, it is going to be the feedforward divided by 1 plus feedforward times feedback, which if you simplify it, it is going to be 1 over s squared plus 3. Now, that guy is in series with 7. So we can multiply that by 7. So this whole thing from here to here is going to be 7 over s squared plus 3. And that with 4 are again in a what? In a feedback. So the whole thing will be seven over s squared plus 3, and again this is negative, so it is going to be 1 plus 7 over s squared plus 3 times 4, which if you simplify, you will get 7 over s squared plus 3 plus 28, so 31. So this is your transfer function of x over f. Yes? Now next time it says what is the transfer function of x over g. So for that, we would neglect f. So here it says what is x over g. So here we set f to be what? 0, which means we neglect this part. We assume that this part does not exist. And so here the summation point goes away and you directly go back here. So since the summation point goes away, then these 4 and 7 are in series, so we can simplify them with one single block that is the product of the two, 28. Then that 28 and this 3, if you look at them, they both come from x and they both end at the same point, but they are just subtracted, right? So the endpoints for both block 3 and block 28 are the same. They are parallel except they are subtracted. So I can simplify these also to a single block that is what? 25. So the first simplification will be like this. That there is a 1 over s here, and then there is the summation point, and then there is this g, and it goes to the next integrator, goes to x, and x comes back to right behind the integrator with a feedback of 25, right? So that's what you get. And now this 25 and 1 over s are in what? In series. So I can again simplify these two, have a single block that is 25 over s, right? And so now you have this one. And I can bring this g here, it doesn't matter. Okay, and now it's a simple feedback. The only difference is here at the feedback, both of these are positive, not negative. Therefore, x over g is going to be this over 1 minus the product of the two, okay? So this is going to be that 1 over s divided by 1 minus 1 over s times 25 over s, which is going to be, if you simplify, there will be an s term, s squared minus 25. Okay? Now, if in any scenario g and f are both given to you, and then they ask you what is x, well, you can find it, right? So maybe they tell you that, for example, f of t is, let's say, t, and then g of t is a delta function. What is x of t? Well, from here you take a Laplace transform, and so f of s is going to be 1 over s squared. You take a Laplace from this, and so g of s is going to be 1. And now you say x over f was something, correct? This it was 7 over s squared plus 31. And then x over g is s over s squared minus 25. So from here I find one output for x, x1 I would call it. So this f, I know it, right? It's 1 over s squared. So it is going to be 7 over s squared plus 31 times f of s, which is 1 over s squared. Then from here, x2 of s, the output due to g is going to be s over s squared minus 25 multiplied by g of s, which is 1. Then you apply inverse Laplace to both. So you will get what? x1 of t, which I'm sure everybody can do at this point. And then you apply an inverse Laplace to this one, and you find x2 of t. And now each one of these is an output because the contribution of f, and this is the output due to contribution of g. So if somebody says, what is the total output? You say the total output is the output due to f plus the output due to g, okay? This is called superposition, and it is only valid if your systems governing differential equations are what? Linear. In this case, we had transfer functions, and transfer functions means the system was linear. So when it's linear, you find individual outputs due to the inputs and then add them together. And that's what I have mentioned for you over here. Okay, we'll do more examples in class.